Now that we have Euler's formula, let's start to look at solutions to systems of differential equations when the roots and the eigenvalues are complex. Let's suppose we have the complex eigenvalue r equal to alpha plus I beta. In reality, this is only the first one. We also have the complex conjugate. R2 would be alpha minus I beta. But for now, let's only consider the positive one. Following what we did before, I'm going to build this vector. I'm going to call it x plus since I'm considering the plus I beta case. This would be E equal to R, which is alpha plus I beta, times T, times the eigenvector. And if we have a complex eigenvalue, our eigenvector will be complex as well. So I'm actually going to break it up into two pieces. A plus IB. Well, we can use that identity that we discussed in the previous video to say that this is e to the alpha t times cosine beta t plus I sine beta t. And then we still have this a plus alpha IB at the end. I'm going to go ahead and FOIL these parentheses. So I have cosine beta t times a plus I sine beta t times a plus I cosine beta t times b, and then we have I squared, so minus sine beta t times b. I want to go ahead and regroup this so I have the real parts together and the imaginary parts together. So I'm going to rewrite it as cosine beta ta minus sine beta tb plus I times sine beta ta plus cosine beta tb. And here we have our actual solution. So I'm going to call this piece right here, this first piece, the real piece. I'm going to call x plus 1. And then this imaginary piece right here, I'm going to call x plus 2, just for simplicity. If we go down a little bit, this should satisfy my differential equation. So if I have my first vector, its derivative, plus I times the derivative of the second vector, it should be equal to a times this thing right here, which is the first one plus I times the second one. I can multiply out that right-hand side, so the left-hand side stays the same. The right-hand side becomes a times my first vector plus a I times the second. I can then set the imaginary parts together and the real parts together. So when I do the real parts, I have the derivative of the first equal to a times that first vector. So this is exactly what my differential equation said. When I do the imaginary parts, I have I times that derivative equal to IA times that second vector. I can divide through by I, and once again I get back to my differential equation. So this implies that I actually don't even need that I in this vector. Instead, I can actually write x plus as e to the alpha t times cosine beta ta minus sine beta TB plus sine beta TA plus cosine beta TB. And once again, this is only our first eigenvalue and eigenvector. We haven't dealt with the fact that we do have a second one floating around here. In particular, the x negative. So if I consider the negative case, the case for r equal to alpha minus I beta, all it's going to do is change some of these signs in here and make them negative when they should be positive or positive when they should be negative. And so once I introduce my c's values, my constants that I'm going to need, then it's actually going to balance out. So my general solution for this is C1 e to the alpha t times cosine beta TA minus sine beta TB. I'm going to move down to the second line because I'm running out of room. But then I would have C2 e to the alpha t times sine beta TA plus cosine beta TB. So this is my general system and my general solution whenever I have a system of differential equations with complex eigenvalues and eigenvectors.